So in this lesson, we're going to talk about what's involved when you titrate a weak acid with a strong base. So we're going to look at the qualitative and the quantitative aspects of that and what needs to be considered. So if you're looking to find out about how a titration works in general, this is not the video for you, and I would suggest that you start by looking at a video that's going to explain to you the basics of titration. But for the purposes of this video, I'm just going to give a quick rundown of some of the equipment we use just as a simple review. So what we have here is a titration apparatus. We have a burette, and the burette contains what we call the titrant, okay, the material that is being used in the titration and added to what we call the analyte. And the analyte is in this usually an Erlenmeyer flask, or in this case a conical flask. Often what we have as our analyte or our titrand is an acid, and our base is in the burette. So in our burette, we would have this base, and we would be slowly adding it to our acid, and in this case, this would be a weak acid, and just seeing how the pH of the acid solution in the conical flask changes as a function of the volume of this base that is added. Okay, so before we begin the calculation portion of this, I want to give a rundown of the main ideas, the qualitative pieces that we need to think about in an acid-base titration where we have a weak acid being titrated with a strong base. So before titration, and so we're talking about before any of our base has been added, then we know that the pH is a function of the acid alone, right? And that should make sense. The weak acid is the only thing contributing to pH at this point because no hydroxide has been added to the solution. And so what makes this different than a titration with a strong acid is that we know that we have a situation where not 100% of our weak acid is going to dissociate. We're only going to end up with about 50% dissociation or less than that. And so that is something that we need to consider. We can't assume that the concentration of our acid is the same as the concentration of our hydronium solutions in hydronium ion in solution. Okay, so in this case, we have to do some calculations involving equilibrium and using our acid ionization constant Ka to figure out pH. So that's the gist of that piece. Okay, and so at the equivalence point is another really significant point in the titration. And so I want to visit with you what an equivalence point is. We would have talked about this in other titration videos, but I think it's a good idea to review. So I want you to remember that at the equivalence point, the number of moles of base, that's our base that we've added, are equivalent to the number of moles of acid that are present, right? And so we need to be, sometimes this is called the stoichiometric point, because in stoichiometrically, we know that there's a 1-to-1 ratio of our acid moles to our base moles at that point, right? So that's important to understand. And so you might be thinking, well, at this point, shouldn't the pH be neutral? Not quite, because we're not talking about the moles of hydronium being equal to the moles of hydroxide. We're talking about moles of the initial acid and the initial base. But we'll get to that. All right, so here we go. So I'm going to start off by just reminding us about what's going on with our weak acid in solution. It's going to dissociate, but not fully. But here's the thing that's going to happen. As we add our base, we're going to slowly add our base from our burette into our conical flask. And every time we do that, that is going to neutralize the hydronium ion that has dissociated. Now, I want you to remember about equilibrium systems and how equilibrium systems work to keep balance. And so both the reverse and forward reaction are happening here. When we add hydroxide to hydronium, we're of course going to form water, and that's going to remove hydronium out of this situation. So it's like, in essence, we're taking hydronium away. And so, well, what happens when you remove a product from an equilibrium system? The system is going to shift in a way to replace that lost species. So as more and more hydroxide is added, the hydronium is going to keep being removed from solution, and so the equilibrium is going to continue to shift to reproduce those hydronium ions. So it forces the equilibrium of the acid to continually shift right. And so at that point, we're going to basically be able to dissociate all of that weak acid, because it's going to be, at the equivalence point, the moles of acid and the moles of base are equivalent, right? And the strong base is going to dissociate 100%. So we have our weak acid and we have our strong base, and we know that the concentration, the number of moles of each of these are going to be this equivalent. And so when I add sodium hydroxide, it will dissociate to produce an equivalent amount of hydroxide as there are sodium hydroxide particles. And so if I'm adding that to my hydronium, every time I add a hydroxide to hydronium, it's pulling out the hydronium out of that solution, and the two of them together are making water, which is going to continue to shift that equilibrium to the product side, right? And so I know that all the acid molecules are eventually going to be forced to dissociate just to replace the missing hydronium ions. And so they're going to be neutralized by the base. And so as I kind of hinted before, you would think that because of that, if all of my hydronium is neutralized, then shouldn't the pH be 7? It's not. But not because of the situation here. So the acid or the base now they've neutralized each other, and so they're not really having an impact on pH. So then why is the pH not neutral? Why is it not neutral at this point? Well, there's more to consider, and this is the piece that is often confusing to students. So at the equivalence point, we've added all the hydroxide that we can, and that has neutralized all of our weak acid hydronium ions, right? The equilibrium was forced to the product side, which has forced our weak acid to dissociate 100%. But the problem is this. The problem is that in producing all of those hydronium, we've also produced this guy, the conjugate base of our weak acid. And that conjugate base is going to go on and experience its own equilibrium situation as a conjugate base. And so it will hydrolyze. And when it hydrolyzes, it forms that weak acid and some hydroxide ions, right, in solution. And you'll remember that a weak acid will have a strong conjugate base. So this equilibrium will actually proceed towards the product side and produce those hydroniums. And it's these hydroniums right here that hydroxides, I should say, that are contributing to the pH of the solution. And that's what we need to work with. Ugh, it's kind of ugly. So the neutralization is going to produce that salt. Okay, this is the anion of the salt that's produced. And those ions, if they hydrolyze, and then they're going to contribute to the pH. And that's the issue that we need to consider. The pH calculations, however, remember that we have to consider both the cation and the anion of the salt. And so our cation in this case would be sodium, and sodium ions don't hydrolyze, so that's not going to contribute to the pH. But if you had a different base, then you might have to consider that as well. So the final significant point in this type of titration is after the equivalence point. And so at this point, what we're seeing in our flask now, all of the original weak acids, hydronium ions have been neutralized, and so we have the pH probably a little bit above neutral because of the anion of the salt that we're looking at, right, that hydrolyzes. But we also have added additional strong base to this situation. And so, in terms of magnitude, that strong base is going to have a much greater impact on the pH overall than that of our hydrolyzed anion in here, right, that we saw at the equivalence point. And so, when we're looking at the pH of the solution, we're going to be looking primarily at the moles of the strong base that we've added to this Erlenmeyer flask, to the original solution. And because of the change in volume, remember that we don't simply have the amount of acid that we started with. We've added a substantial amount of base at this point, and so that's going to contribute to the volume of that solution. And so we need to consider both the moles of base that have been added as well as the total volume of solution when doing making concentration calculations and then assessing pH. All right, so let's talk now about a typical type of question that you might be asked to complete. So let me read it out for you. It says a titration is performed where 20 milliliters of a 0.6 mole per liter acetic acid is titrated with 0.3 moles per liter sodium hydroxide. So acetic acid, we would want to verify that it's a weak acid, and you can check that because it would have an acid ionization constant Ka associated with it. And sodium hydroxide is a strong base, and it's a strong base because if you look at a solubility chart, sodium compounds are always highly soluble, so sodium hydroxide is going to dissociate 100% solution. And so, as we highlighted, there are 3 significant points in the titration that need to be considered, and we've looked at it qualitatively, but we also need to look at it quantitatively. So before the titration begins, we want to know the pH at the equivalence point, and we want to know after the equivalence point, after a certain amount of base has been added. And so these essentially constitute 3 data points if we were trying to build a titration curve. And I would suggest that these are a great starting point to constructing that titration curve. And then once you have those key data points, you can sort of work around them to fill in more of the graph to kind of highlight that typical titration curve shape. So let's take a look at this. So I've just pulled out a graph, a generic graph of a titration of a weak acid with a strong base. And of course, the values here would differ depending on which weak acid you use and which strong base you used. But here you can see the 3 data points we discussed, that initial concentration, or initial pH rather, that's a function of your weak acid. And then you have the equivalence point where the pH is a function of the salt that is produced in its own equilibrium. And then after the equivalence point, the pH is a function of the additional strong base that's been added to solution in conjunction with the total volume of solution. And so in the next part of this video, I really want to break down the types of calculations we need to do at each stage of this titration, as outlined in the question. So that's where we're going next. Okay, so I've switched to my handy dandy Jamboard where I can write some stuff down here. And so this is the question that we just looked at. We're going to start by looking at part A of this question, which is, well, what is going on with the pH before the titration begins? And so you'll remember that the only species contributing to the pH is this weak acid. And so because it's a weak acid, we need to look at this from an equilibrium standpoint. And that means that there's an icebox involved. All right, so let's do this. I'm going to start by just simply writing out the reaction equation, the relevant reaction equation. And that is for that weak acid. So I've got my acetic acid, HC2H3O2. And I'm going to kind of leave out subscripts because all of this is going to be aqueous anyway. Our water is liquid. So I'm going to include that because that's going to matter when we fill out our icebox. And that's going to dissociate to produce some hydronium ions in addition to my conjugate base, the acetate ion. Let me squeeze this in here. Okay, and so constructing my icebox is going to look like this. So I've got, I want to know my initial concentration, and that's in moles per liter, my change in concentration in moles per liter, and then finally my equilibrium concentrations. And so some of these are going to be expressions. And so I should note before we do anything else that my Ka, I've looked up the Ka for acetic acid, and it is 1.8 times 10 to the negative 5. And that's just, usually there's a table in the back of a textbook where you can source out that information. Okay, and so let's talk about initially. So first of all, the concentration of liquids and solids are unchanging and don't contribute to this equilibrium situation. but my initial concentration of the acid is 0.600 moles per liter. And my initial concentration before any dissociation is 0.000 moles per liter of each of those ions. Okay, and so I know that over time, as this equilibrium proceeds, that I'm going to see a decrease in my reactant and then an increase in my ion products. And so I'm going to represent that change in the amount of decrease as using the variable x, and x. And remember that in each of these I have a 1:1:1 ratio, which is why there is a coefficient of 1 beside each of these x's. Okay, and then so finally the equilibrium expressions are a function of my initial concentration plus my change. And so I'm going to just add these two expressions together. So 0.600 minus x. Over here I have 0 plus x gives me x. 0 plus x again gives me x. And so now I'm going to use these equilibrium expressions for my icebox to help me construct an acid ionization law for this situation. Okay, and so I've taken the liberty of copying a little what we wrote on the last slide so that it's there visually for us, but now we're going to write out that equilibrium law. So I know that in general our acid ionization constant is equal to the concentration of our products raised to the exponent of their coefficient. So in this case I've got my hydronium ion multiplied by my acetate ion divided by the concentration of my acetic acid. And now, you know, in my icebox, I've filled out some expressions for the equilibrium concentrations, and I also sourced out that Ka. So I'm going to go ahead and substitute my known information into this equation. So 1.8 times 10 to the negative 5 is equal to, and I've got x times x. So that is going to mean x squared. So I'm just going to go ahead and write that as x squared divided by 0.600 minus x. Okay, so this is not the time that I want to talk about the 100 rule, but here's the thing. I know that this Ka value is very, very, very small. And so if you've watched my past videos, you know that when your ionization, when your equilibrium constant is very, very small, that means that not a whole lot of product is going to form, right? And that makes sense. This is a weak acid. It's not going to dissociate a lot. So in other words, this amount here, x, is going to be very, very small in magnitude compared to the magnitude of the initial concentration. So, so then what I can do mathematically is I can just get rid of it because it's going to be so insignificant that it's not going to matter. And it's going to make my life a whole lot easier because now this becomes a very easy equation to solve. So I'm going to go through the math really quickly. I'm going to multiply this 0.6 times my 1.8 times 10 to the negative 5. And so that's going to give me x squared is equal to 1.1 times 10 to the negative 5. And again, I'm just rounding to two significant digits here in this case, but I'm not truncating the original value. So I'm going to square root this to find out the value of x. So I'm getting that x has a value of let's say 3.3 times 10 to the negative 3 moles per liter. And so if we go and we check out, well, what does x actually represent here? What is this variable x actually representing? Well, and how's that going to help me figure out the pH, which is my goal? Well, you'll remember that my hydronium ion concentration at equilibrium was represented by that variable x. And so because I know that, I can go ahead and say, well, now that means that this is my hydronium ion concentration at equilibrium. And that's going to allow me to calculate pH. So I'm going to call this kind of like this is step number 1, this is step number 2, And now I'm about to go through step number 3, which is, of course, to calculate the pH. And how do we do that? Well, the pH is equal to the negative log base 10 of our hydronium ion concentration. So negative log of 3.3 times 10 to the negative 3, and of course, oopsies, and of course I've not truncated the original value. I'm still holding that in my calculator, so I'm going to go ahead and work that out, and I'm getting a value of, 2.48. And so, that makes sense. That's a pH that makes sense if I've got a weak acid and I haven't added any base yet. Okay, so on to the next step. Before we move on, I just want to highlight for you, remember that what we're trying to accomplish here potentially is to create a graph of a titration curve. And so we're building data points here, right? So if I can sort of think of what we've done so far as starting our table of values, where we're looking at the volume of base, okay, potentially in milliliters, versus the pH, right? So how is the pH affected by the volume of base? And so at this point in the titration, how much base have we added? Well, we've added none, and we know that our pH is 2.48. So that's a data point that we could use in constructing our titration curve. And going through to parts B and part C of this question will help us fill out 2 more data points to begin creating that curve. All right, let's examine what's going on at the equivalence point. So you'll recall from an earlier part in the video that the equivalence point, or the stoichiometric point, is the point where the number of moles of my acid are equal to the number of moles of my base. And so the question doesn't tell us what volume of base has been added to this situation. And so we've got to that is really important for us to figure out before we can move on. So I'm just going to write out the neutralization reaction that's happening. So here's my weak acid, my acetic acid, and here's my strong base, my sodium hydroxide. And in this double displacement reaction, I'm going to end up with sodium acetate and water. And at the equivalence point, I know the moles of acid are equal to the moles of base. And so let's try to figure out what volume of base has been added here. And so I know that my initial concentration of my acid is 0.600 moles per liter. And I know my concentration of base is 0.600 moles per liter. And that I've added 20 milliliters of my acid to my conical flask over here. So what I'm trying to figure out is, well, what volume of base has been added at the equivalence point. So let's do a little bit of stoichiometry. All right, so I know that my concentration of my acid is equal to the number of moles of the acid divided by its volume. So if I rearrange that equation, looking to isolate for acid, then that's going to be equal to my concentration times my volume. And so let's take a look at that. I know that I have 0.600 moles per liter times my volume of 20 milliliters, or 0.0200 liters. And so I can see here that my dimensions will cancel out, the liters will cancel, and I'll be left with a number of moles. And so the number of moles that I have of acid are 0.0120 moles. And so I know that that is also equal to the moles of my base, because at the equivalence point, those are equivalent by definition, right? So I know that I have 0.0120 moles of my base, my sodium hydroxide. And so if I'm going to number these, I'm going to say, well, this is part number 1, this is part number 2, and then the third part so far is going to be to figure out, well, what volume of my base did I add? And so again, we know that the concentration of my base is equal to the number of moles of my base divided by the volume. Rearranging for volume, I get that the volume of base is going to be equal to my number of moles divided by the concentration. And so in this case, the 0.0120 moles divided by 0.300 moles per liter, running out of real estate. My volume of my base is equal to 40.0 milliliters. So what does that actually mean? So that means that I've added 40 milliliters at this point of my titrant into my conical flask, into the acid. That is how many, what volume of my base is required to reach that equivalence point. And so that's important for us to know moving forward. So let's just kind of keep that value in mind as we proceed through the rest of this question. And this part is the lengthy part, and it is quite involved. So you might have to watch this a couple of times to help make all the pieces kind of merge together. Okay, so before we go on to the next steps involved, I'm just going to kind of make note of the fact that at the equivalence point, we've added 40 milliliters of base. Okay, so we're just going to kind of keep that in mind as we proceed. And so I'm going to call this step, I guess this is step number 3 at this point. Now, in the earlier part of my video, we talked sort of qualitatively about the equivalence point and what's contributing to pH. So at the equivalence point, we have neutralized all of the acid with the base, but what we have going on here is we have the salt that is contributing to the pH. And so, if my acid has this dissociation, Ha plus H2O, going to produce A minus plus H3O plus, and all of the bases sort of knocked out these guys, but now I have this salt, anion of the salt, that's contributing to pH, and that's really what it is I need to think about at this point. So I'm going to write out this hydrolysis. So I've got my conjugate base plus water is going to react, and if it's a base, remember bases are proton acceptors, so it's going to form Ha, and then my water is going to act as the proton donor, as the acid, and it's going to, and as a result, hydroxide ions are going to form. Okay, and so the issue is now is that what I have here is a base dissociation, right? And so I need to know, in order to proceed forward, I need to know a couple of pieces of information. I know that I have the Ka for this guy, but what I really need is the Kb, the base ionization constant for A minus. And so you'll maybe remember, and this, this should go this is in an earlier video, not the time or place to go through that here, but you will remember that there's a relationship that exists between Ka and Kb, where Kw is equal to Ka times Kb, where Ka and Kb are acid-base conjugates. And so Kw at 25 degrees Celsius has a value of 1.0 times 10 to the negative 14. Our Ka for Ha, you'll remember from our earlier work, was 1.8 times 10 to the negative 5. And so that's going to get substituted in over here for Ka. And so that's what I'm going to do next. So 1.8 times 10 to the negative 5 times Kb. And so solving for Kb, I get a value of a 5.6 times 10 to the negative 10. Okay, and so now that I have this Kb value, I'm going to go ahead and create an ice chart with this weak base. And that's going to give me some equilibrium expressions that I can use to solve for the concentration of hydroxide at equilibrium. Because remember our conversation earlier, this right here is what's actually contributing to the pH of what is in this conical flask. Our acid, original acid, hydronium, has been neutralized by the hydroxide in our strong base completely. So it is this hydroxide here, its concentration in solution, that's going to be affecting the pH. So that's what we need to look at next. So I've taken the liberty of going ahead and just jotting down some of the information from the previous slide, which is that we still have the 40 mils of base that's been added to our conical flask. Our Kb value we calculated, and I've set up our ice chart. Now, remember that our ice chart involves looking at concentrations of species. And so what I need to figure out first is the concentration of my acetate ion in solution. And the acetate ion concentration, the only thing contributing to that is the is coming from that weak acid that we started with, right? And so, but the problem is that we can't really look at the initial concentration of acetic acid because we've added a boatload of base. And so we started with 20 milliliters of acid, and we added 40 mils of base. So we have a total of 60 milliliters here in our conical flask. And so that's going to dilute the acetate that's in that solution in the conical flask. So we need to work that out first. Okay, and so our acetate, the C2H3O2 minus, is coming from our initial concentration of acetic acid, but it's been diluted. So I no longer have 20 mils of this concentration. I've diluted it by adding the base, and so I need to figure out the new concentration of that acetate. And so I'm going to go ahead and do that. And so I know that the concentration of my acetate is going to be equal to the number of moles of acetate that I have divided by the volume, total volume. And so the number of moles of acetate are going to be equal to the moles of my acid, because remember that the equilibrium for that acetic acid got pushed and pushed and pushed, so that we saw all of the acetic acid dissociate as the base was added. And so we know that in 0.600 moles per liter, we have 20 milliliters of it, so 0.0200 liters, that's going to give us 0.0120 moles, right? And we did that calculation before, just showing you again. So we have 0.0120 moles of acetate divided by a new volume of 60 milliliters, and that's going to give me a concentration that's going to go in my ice chart right here. And that ends up being 0.200 moles per liter. Okay, so now let me fill out my ice chart. So I know that I'm starting with 0.200 moles per liter. My water's concentration remains constant. And initially I'm going to have before any dissociation happens, I'm going to have 0 moles of hydroxide or acetic acid. So the equilibrium is, of course, going to shift to the right to balance things, and so I'm going to end up with a decrease of acetate, and I'm going to, qualify that as using the variable x. I'm going to say that I'm going to see an increase in the concentration of products. So that gives me some beautiful equilibrium expressions that I'm going to use in my base ionization, that equilibrium law. Okay, and so I think I'm just about ready to start with that piece. And this is going to look a lot like what we did before. And so I know that Kb, in this case, is going to be equal to the concentration of my products raised to the exponent of their coefficients in the balanced chemical equation divided by that of my reactants. In this case, it's the acetate ion. That's going to give me an expression, and I know my Kb from up here. So I'm just going to take that value and substitute it in. I'm going to end up with x squared over 0.200 minus x. Now I can simplify the math in this case because my base ionization constant is really, really small, which means that, this reaction proceeding in the forward direction is not going to go very far before the equilibrium reverses. And so that means that this amount x here is negligible, and I can sort of just simplify the math. And so when I simplify the math, what I can do is just solve this for x, as I showed in an earlier step. So I'm just going to go ahead and solve for x in this. And the value of x ends up being 1.054 times 10 to the negative 5. I've carried some extra digits here. And now that I have that value, I know that that represents also, right, because remember, well, what is x? What is x representing? It's representing the concentration of hydroxide ion in solution. So this is equal to my hydroxide ion concentration. And that's how I'm going to get pH eventually. And so I'm going to move that to the next slide and carry on. And so the goal of this question was, of course, to figure out the pH, right? I can't calculate pH directly from my hydroxide ion concentration, so I need to figure out my pOH first. So pOH is equal to the negative log of my hydroxide ion concentration. And so the negative log of 1.054 times 10 to the negative 5 is going to give me a value of 4.98. And so I know that there's this handy relationship here where I know that pH plus pOH is equal to 14. And so subtracting that pOH value from 14, the 4.98, I'm going to get a value of 9.02 as my pH at the equivalence point. So remember, we've been sort of accumulating these data points for our titration curve, right, by doing these calculations. So here, if I'm looking at the volume of my base that's been added versus the pH, I had that no base added gave me a pH of 2.48. And now I have a second data point, which is that at 40 milliliters, my pH is now suddenly at 9.02. So quite a sharp rise there. And so it would be suitable to find some data points in between those two values. But here we are, and that's a good kind of place to start. Okay, so our last thing that we're going to do is we're going to look at, well, what happens after we pass the equivalence point. And this piece is a little bit trickier than you might think. So let's break it down. So at this point, the question is saying, well, what is the pH after I've added 60 milliliters of base? And you'll remember that in my conical flask, I started with 20 milliliters of acid. Okay, now the thing is that the base's concentration is not the same as that of the acid. So I need to do a little bit of stoichiometry to figure out, well, what volume of base needed to be added. And so in the last step, I actually figured that out. So I know that the volume of my base that was required to neutralize was 40 milliliters, right, at the equivalence point. And so if I've added at this point 60 milliliters, and it took 40 milliliters of that base to neutralize all of my acid, then that means there's a surplus now of 20 milliliters of base left in the conical flask to contribute to the pH. Okay, so let me jot this down, and this is like the neutralization, right? So, or I should say that's like your equivalence point value. Okay, and so now I have that, and so I need to figure out, well, if my initial concentration of base was 3.3 moles per liter, and I have added an extra 20 milliliters of it, how many moles are in that? Because I need to get the number of moles in my new volume of solution that I've added in total. Okay, so we'll call this step number 1. Okay, and then step number 2 is going to be to say, all right, well, my number of moles of base are going to be the initial concentration, 0.300 moles per liter, times the volume of excess, 0.0200 liters. And that's going to give me 6.00 times 10 to the power of -3 moles of sodium hydroxide. But the thing is I actually don't have that in 20 milliliters anymore. I've got it in a much larger volume of solution. Now, if I've added, I'll call this step number 3, if I have added 60 the volume total now in my conical flask is going to be the 20 milliliters of my acid that was originally there before I added any base, plus the 60 milliliters of my base that was added at this point, right? So that's going to give me a new total volume, and that's in my conical flask here, of 80 mils. Okay, so I've got 6 times 10 to the -3 moles in 80 milliliters of solution, and so I need to work out my new concentration. So then we're going to call that step 4. And step 4 is going to be the concentration of my base is equal to the 6.00 times 10 to the -3 moles divided by the 0.0800 liters, giving me a concentration of 0.075 moles per liter of my base. And so you'll remember that this is a strong base, so it's going to dissociate 100%. This is a strong base. So I don't need to look at any equilibrium calculations at this point. And so the last thing I'm going to do here is I'm going to say, well, my 5th step is going to be to figure out the pOH, and that's going to allow me to figure out the pH. So the pOH is going to be equal to the negative log of my hydroxide ion concentration, and that is this value right here. So substituting that in, I get a value for my pOH of 1.12. And hopefully you recognize that that does not make sense as a pH, so we need to do more work, and we know that the pH plus the pOH is equal to 14, so 14 minus 1.12 is going to give me my pH at this point, and this one is in line, and this one makes sense, so around 12.9-ish, 12.87, or 88, I guess I would say. Okay, and so that is past the equivalence point. So now if we really look at things, what we've got is we've got our table of values with 3 distinct points. We've got our volume of base that we've added. We've got our pH, right? We had the 0 milliliters, and that was a pH of 2.448. At the equivalence point, we had 40 mils added, and that gave us a pH of 9.02. And now we've added 60 mils, and that gives us a pH of 12.88. Okay, so great starting point for us to fill in some other data points. We just need to remember that before and after the equivalence point, but before the after the equivalence point, it's the base that's going to contribute. So the calculation would look a lot like this. Okay, so that's quite a lengthy lesson with lots of important details to consider. You may need to revisit the video to be clear on some of these ideas and help them to gel together, but I hope that helps. Please reach out if you have any questions.